Question 1 is fairly straightforward. These are basically just definitions straight out of your textbook. Moving on to question 2.1. Here you have a body moved across a frictionless horizontal plane by a constant horizontal force. Now, from Newton's first or second law, if you have a horizontal force, constant horizontal force acting, there will be an acceleration. However, because the force is constant, that acceleration will be constant as well, and hence will not increase. Because there will be an acceleration, velocity will change. Because velocity changes, momentum will change. And also because velocity changes, kinetic energy will change. So the only quantity that will not increase is acceleration, so the answer is C. One of the easiest ways to access the answer to question 2.2 is to look at the situation, give it some thought as to what you think the solution should look like, and then look at the graphs and choose the graph that best matches your expectation of what you expect the motion to be like. Let's start looking at the section RS, which is frictionless and which is flat. Because it's flat, there will be no component of gravity parallel to the surface, and because there's no friction, there'll be no net force in the parallel direction. In which case, there's no net force, so the acceleration is 0, so your velocity should be constant. This rules out C as an option, leaving you with A, B, and D. Now, from P to R, there is friction. Let's look at Q to R only. From Q to R, your surface is flat, so there's friction slowing your object down, but there's no component of gravity acting parallel to the slope speeding it up. So it's definitely going to slow down, so you need to see a decreasing velocity. Okay. Let's look at P to Q now. P to Q, your object is on a slope. Yes, it experiences friction, but it's reasonable to assume here that the acceleration caused by gravity on the slope, or rather the component of gravity parallel to the slope, will overcome friction, and overall your object will accelerate. It starts from rest, and it starts moving, so this matches our assumption. So you need to find a graph that says from P to Q, your velocity is increasing, and from Q to R, your velocity is decreasing. And the graph that best matches that is the graph of A. In question 2.3, the trick is to realize that the distances x and 2x are actually irrelevant to the problem. The distance through which each trolley passes doesn't affect its eventual kinetic energy. What does affect its eventual kinetic energy is the height through which it passes, and that is the same for both trolleys. So now the only thing that is different between the two trolleys is their masses. Looking at the formula for gravitational potential energy, EP equals mgh, you can see that the gravitational potential energy is directly proportional to both the mass and the height of the object. Because these objects move through the same height, the only thing that can affect their gravitational potential energy are their masses. Because object Q has double the mass of object P, it has double the potential energy, and therefore, when it reaches the bottom of the ramp, it will have double the kinetic energy, and this matches the answer for B. Question 2.4. The local acceleration due to gravity, little g, with the value of 9.8 meters per second squared near the surface of the Earth, is approximately constant for any object, regardless of its mass. So your body's gravitational acceleration is independent of its mass, giving you D as the answer. Question 2.5 requires you to play around with a couple of units in terms of working out what is equivalent to the watt, and therefore which one is not equivalent. Option C is the easiest one to eliminate at this point, because that basically comes from the definition of the watt. A watt is your unit for power, which is energy consumed per unit time. Units for energy, the joule. Units for time, the second. So the watt is equivalent to a joule per second. This knocks out C as a potential candidate. Let's look at option D. A Newton times a meter is actually equivalent to the joule. And the easiest way to see that is through the formula W equals F delta X. I'm leaving out the factor of cos theta here. This is your formula for work. When a force is exerted over an object over a certain distance, the work done is the force, measured in newtons, multiplied by the distance, measured in meters. Now work is the transfer of energy, so it must be measured in energy, units of energy as well. That's the joule. So a newton meter is equivalent to a joule, and then D is equivalent to a joule per second, so that is equivalent to the watt. So we can eliminate D as well. And now it just comes down to looking and choosing between A and B. You can see that A and B are almost identical. The only difference is the factor of s to the minus 3 in A and the factor of s to the minus 2 in B. How do we choose between these? It's not an easy one. What you need to see is that in both A and B, we have Newton's second law giving us the unit of the Newton. From F equals ma, a Newton is equal to a kilogram, the unit for mass, multiplied by meters per second squared, the unit for acceleration. So now let's look at A and B a little bit more closely. A and B agree on the kilogram meter squared. Where does the meter squared come in? It comes in with an extra factor of m, another meter, from the delta x that you use in your work equation. Work is force multiplied by displacement. So that means we just need to choose between s to the minus 3 and s to the minus 2. We see here in this expression for Newton's second law that the Newton has s to the minus 2 in it. So when we calculate the work done, force times displacement, the Newton will give us s to the minus 2, but what we're looking for is something that is equivalent to the watt, which is units of work, or units of energy, per second. So we need an extra factor of s to the minus 1. So A, with this extra factor of s to the minus 1, giving us overall s to the minus 3, is correct, and that means we exclude it as an option to this question, because this question is looking for something that is not equivalent to the watt, leaving B as the only choice. Question 2.6 can either be done intuitively, or if you're making use of the relative velocity formula, you need to choose a particular direction as positive. In this particular sample solution, I've chosen east as the positive direction. And then you use your formula. The relative velocity between A and B, that's how you read this quantity on the left, is equal to the velocity of A minus the velocity of B. The velocity of A, using east as the positive direction, is positive 110. The velocity of B, because car B is traveling at 80 kilometers per hour west, will be negative 80. So we have negative 80, meaning the relative velocity between A and B, or car A relative to car B, is 190 kilometers per hour in the positive direction, which means A is the correct answer because the positive direction we identified as east.